Okay, let's see, what I wanted to do today was finish talking about the nonlinear modeling part of the book and give you an example of doing one of those types of models. So I'm going to show you an example of the spline-based model. Remember that these nonlinear models they are extensions of a linear model, like a simple linear regression model or logistic regression model, anything where we have beta 0 times a covariate, or beta times covariates. Extension of that to a case where there's potentially curvy relationships between the predictor and the response. That can be really useful in cases where the nature of your data is that it is a curvy relationship. So imagine you had measurements over time, for example, of a numeric variable, and it goes in cycles, or it goes through different periods where it can take arbitrary values. It's not a linear necessarily relationship. So anyway, nonlinear models are useful in their own right. So what I wanted to do was go to the Hall of Fame data. I have a couple of additional predictive model examples for this data that I wanted to go through. And I'm going to add a little bit for doing a spline-based model. Let me get our notes back for this particular topic. Moving beyond linearity. We're going to wrap this up, hopefully today, and then begin on the next chapter, which is tree-based methods. Okay, let's go to nonlinear. And the whole point of this chapter is to illustrate a variety of ways that you can incorporate nonlinear relationships. It doesn't have to be a smooth function. It could be a step function. The simplest case, arguably, is polynomials. That's where we started last time. Instead of just having a linear function of x, you could have a quadratic function of x. Splines and local regression are examples of what you'd call modern regression. So it's not least squares regression. It's a more data adaptive type. It's more flexible. It allows for curvy relationships. Let me say something about interpretability, though. A linear regression model where you have a covariate times a beta coefficient, I've said that's relatively easy to interpret and tell somebody what's the effect of this predictor variable. Every 1 unit increase in it associated with a beta mean change in the response. That's interpretable. If you move to a nonlinear model, whether it's a polynomial model or one of these more sophisticated ones, the interpretation becomes much harder, if not impossible. What's the effect of x is hard to say if x goes into the model with some curve. Linear is simple, curvy is not. So I'll reiterate something I've said before. In the context of predictive modeling, which is what the second half of the class has been all about, there is a trade-off between interpretability and accuracy sometimes. It is sometimes the case that with complex relationships, a more complex model will achieve better accuracy. But the more complex models come at the price of less interpretability. So depending on the situation, you may care more or less about interpretability. Certain situations, the goal may simply be to predict with as high of accuracy as possible. That's all we really care about. We're not interested in trying to learn about what makes things tick. I just want to be able to predict accurately. So keep in mind, there's this spectrum from simpler models to more complex models. Generally speaking, simpler models are more interpretable. They're also more stable in terms of the variability of your predictions. Simpler models are more stable. More complex models can tend to be more accurate. They're less interpretable, and they tend to be more variable. Let me go to the section where they talk about splines. Okay, suppose we have one numeric variable that we want to predict, and we have one numeric predictor variable that we want to use. Let me draw it on our whiteboard. We have a numeric response and we have a single numeric predictor. And the goal is to model y in terms of x. Suppose we have data and we make a scatter plot of our observed x and y pairs. And suppose we see a pattern like this that in particular is not linear. So I would like to build a regression type model, y written as some function of x plus random error. I think, though, that a linear regression model will not be optimal because I can see nonlinearity in my data. So instead, we could consider a variety of things. We could introduce a polynomial term. More generally, we can kind of expand x into some specially designed functions that parameterize a curve. So suppose that b1 of x was just x, and suppose b2 of x was just x squared, and b p of x was x to the p. Then this is just a cryptic way of writing a polynomial model. But the idea of splines is to replace what would otherwise be exponentiated values of x with specially designed functions that enable us to say, I want to fit to my data a curve that's not a specifically parameterized curve. It's not a quadratic polynomial or anything. It's going to be data derived or data dependent. The data is going to tell us what the shape is, rather than us saying it's linear and so fit a linear curve. So we want to express y in such a way that allows for an arbitrary curve. That's the idea. This is what a spline model looks like. Transforming x into different functions that allow for the curvature we want. As I said, one example would be just to put b of x equals x to a particular power. But it can be, yeah, so the spline thing is actually more complicated than this. So let me just say the goal of writing a model with a spline representation, or the way we do it, I guess I should say, is to say y is equal to a model matrix times a vector of coefficients. And the columns of x, the model matrix, are these B functions. So if I wanted to fit a p-dimensional spline, then x would be an n by p model matrix, and the columns of x would be these specially designed functions, the b's. But the way that they are constructed and parameterized enables this curvy function estimation. So behind the scenes, I guess, what you could say it's doing is picking bin locations that are called knots, and within these bins, fitting a curve of a particular type with what are called natural cubic splines or cubic splines in between the endpoints, inside these little bins. We fit a cubic polynomial. And then we impose a restriction that the cubic polynomials that are estimated in each bin have to be continuous at the interval endpoints, so that everything connects and also is smooth overall. So that's all I want to say about what a spline is, but now I want to show you how you can use one. So let's look at the Hall of Fame data to do that. We're going to pick let's see. Let's pick actually I think I'll do a little simulation. I'll just make up some data to illustrate this. So we're going to make up a regression model of the form y is a curvy function of x. So I'm going to make up my own x values. Let's suppose we have 100 observations, sample size of 100, and I'm going to randomly generate my predictor variable from a uniform distribution between 0 and 1. And I'm going to generate my response from a model. I'm simulating data under an arbitrarily chosen model, and then we're going to use a spline-based model to estimate the truth. It's a simulation in the sense that we're going to know what the actual relationships are. We're going to know what the true model is, and we can illustrate how does the B-spline thing work as an estimation routine. We'll be able to plot, here's the real relationship, and then here's the estimated relationship with a spline. The thing I want to illustrate with using a spline is that it allows you to do a regression model. You can use LM to just do a usual linear model in R. But instead of getting beta coefficients back for a linear model, you get beta coefficients back for this spline representation. Those are not very easy to interpret, but you now have a model you can use to make predictions that has a nice curve in it. So you can make good predictions, and you can draw a picture. You could make a scatter plot of your data and overlay the estimated curve. We're not going to be so interested in the beta coefficients as in the model's overall ability to predict, and we want to make a picture of the estimated curve. So I don't want to spend too much time on the simulation. Let me just do this real quick. We're going to say y is let's say y is going to be a cubic polynomial And the coefficients of the model I'm going to use to simulate from is intercept of 0, a coefficient for x of 0.5, coefficient for x squared of 0.4, and a coefficient for x cubed of minus 0.1. I'm going to write models in this form, y equals x beta plus epsilon, where x is a design matrix, model matrix. I'll show you what I mean by that in just a second, but it's a quick way to simulate data from a model. So my model matrix is a quick way to get it. I don't expect you to be able to do this, but a quick way to get what I want, and I'll show you what it looks like in a second, is this way. Let's do data frame. Okay, trying to simulate data, I want to use a nonlinear model as the truth. So we're going to have that the expected value of the response is equal to beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed. And I'm going to simulate from that to get what look like real data so that I can then illustrate the spline model. I'm going to simulate from this with a sample size of 100. I picked beta 0, beta 1, beta 2, beta 3. And now to actually generate the response, we have 100 randomly generated x values. Now to generate the response, I'm going to use this model representation here. A design matrix times a vector of coefficients plus this needs to be a vector of random error terms that we'll take from a normal distribution. So it looks like this. We're going to do model matrix, matrix multiply by beta, and then the random error terms will say normally distributed. I need n of them. The mean of the error terms is 0, and the residual standard deviation, I'll call it SG or sigma, is equal to 1. Could be equal to anything we want. We're doing a simulation. I picked 1. I randomly created some x's. I parameterized a cubic polynomial to represent the real relationship between y and x. And then I simulated a data set from that model. At this point, let me put a little documentation. Let's parameterize the model to simulate from. And this is use our model to simulate a data set. So now we have x and y, and let's make a picture of them. These are non-linearly related, so a linear regression model is not ideal. Run all of this. That's a lot of variability. In order to make it so I can see things a little better, I'm going to decrease this residual standard deviation. Let's make it 0.25. This will make it easier to see the mean relationship. So now I can actually kind of see a curve. But these are my simulated data. It's as if I collected a data set of size 100, and it just happens that they came from the actual population level model was this cubic polynomial. Linear regression model, we could do it. Let's say linear regression model, fit linear. And in the usual way, use LM, response, tilde, predictor. And how about we overlay the fitted curve, the fitted model, based on the linear model? I think you can just say lines and then the fitted object. Otherwise, I could go get the beta 0 and beta 1 estimates and explicitly say, draw the line with this intercept and that slope. Let's see what happens if I just use lines. I'll make it a color. Make it a little bit wider so we can see it. Okay, so I think I need to try harder to get the lines added. Here's fit linear. The summary of fit linear shows us the usual regression output. Here's the estimated intercept, beta 0 hat. Here's the estimated slope, beta 1 hat. If I want to plot the fitted curve, then I just want to draw the line with intercept minus 0.065 and slope 0.856. I could just code that. I could say AB line and type them in. I'll just, let's see. How about we extract the beta hat estimates? Beta hat is available from the fitted object. Here are the pieces that I can extract from the fitted object. There's an element called coefficients. And if I say fit linear $coefficients, I get what I want, beta 0 and beta 1. So I'm going to store those so that I can refer to them in a second. Fit linear coefficients. Now to overlay the fitted line, I can use the AB line function. That takes two arguments, one for the intercept, one for the slope. The estimated intercept is the first element of beta hat, and the estimated slope is the second element of beta hat. Does anybody know how I can make this a separate panel so that we can see it more clearly? I'm not used to using RStudio. It's just hard to see. I'd like to make it like... Oh, okay, good. Thanks. Let's overlay. Okay, that's the best fitting line. Just for illustrating what the true model is, how about we overlay the true curve as well? the true curve that we simulated from was this cubic polynomial. And again, you don't have to know how to do this, but follow along. There's a function that allows you to draw an arbitrary curve. Let me make sure I get the syntax right. But for example, if you just wanted to plot y equals x squared, you can call the curve function. So curve needs an expression that can be the name of a function. So what I'm going to do is write my own function to implement the model I simulated from. So how about I put plot simulated data and overlay the simulation model. So my plot function is a function of x, and what it does is compute x times beta. So I think inside here I need to reproduce this stuff. And then I can return x times beta. If that worked. I think that worked. Now let's add this line. Okay. So it's not real dramatic in this case that the truth is not linear. If we fiddled with those beta coefficients that we use to simulate from, we could make that more and more curvy. So I'll try to do that by manipulating these, see if we can make it more obviously nonlinear. I guess that's a little bit better. You can see a little bit of departure on the left end. I wish I could do it, get it to be more obviously not linear. There we go. Okay. So we simulated data from the green curve. Y on average is equal to that function of x. We fit a linear regression model. That's the red line, and it didn't capture really the essence of the data. So as an alternative, consider nonlinear models. A nonlinear linear model using what's called a natural cubic spline. Splines are a general way of parameterizing curves. There's some math about optimal ways of doing that. And among all possible ways of defining a curve, what's called a natural cubic spline has some optimal characteristics. So when in doubt, if you want a curvy model, while there are many ways to parameterize a curvy model, a natural cubic spline is a good choice. And there are functions in R for doing that easily. So I'm going to show you the NS function in particular for natural cubic splines. The way that we do this is, again, using LM. So I can use LM as just like we did above. The operations for estimating the coefficients are the same as least squares. It's just that we use a design matrix, that capital X, that's carefully defined to allow the curve for a curvy function, not just a linear function. So I need to eventually write LM y tilde, and the way that I specify I want a natural cubic spline representation of my predictor is by wrapping it in the NS function. So this is saying do a least squares regression model, but it's not a linear model because I'm saying model my response with a, quote, natural cubic spline defined for X. So this is a slick way with one little bit of code to parameterize a linear regression model that has curviness for X. Let's, the NS function, the spline functions come together in a package called Splines. Might have to go install that one. Nope, okay. I think Splines comes with the default installation of R. So having libraried that in, let's look at the help file for the NS function. This B-Spline basis matrix is a mouthful, and it refers to the carefully constructed capital X design matrix. Those little functions that I mentioned at the beginning, the B of X, B1 of X, B2 of X, a B-Spline basis matrix is the design matrix with the carefully constructed columns. The math is beyond the scope of this class. So for our purposes, we're going to take our numeric predictor variable and use this function to build a carefully constructed design matrix. So here's the usage in S. You tell it your predictor variable. Here we have one predictor variable. If I had two predictor variables, I could have a separate cubic spline for that one by just using NS again. And you could also have an interaction between the two. So imagine I'm illustrating just with one predictor variable, very simple case. But if you have lots of predictor variables and you want all of them to have curves, and potentially you want the curve for one variable to be able to depend on the value of another variable, then just like in a linear regression model, you might consider an interaction. You can do interactions with these splines. So they can be really useful with complex data. So I need to finish writing this NS command. Help file says NS, first argument is your predictor. Second argument is called DF. That's standing for degrees of freedom. And the idea behind the degrees of freedom of a spline is how wiggly is it allowed to be. We're essentially trying to fit a curve to a scatter plot, and between the extreme of a linear curve and interpolating the scatter plot exactly, how wiggly do I want my curve to be allowed to be? That's measured by, in the spline literature, what's called degrees of freedom. So I need to specify the number of degrees of freedom. There's not a perfect choice for this. I'm going to pick 5 just because I've used that a lot in practice. Seems to be a good choice as a general strategy, but suppose you were building a predictive model with data like these and you wanted to use a spline-based model, but you weren't sure how many degrees of freedom to use. You could use train test split or cross-validation to tune with respect to that. So let's illustrate a natural cubic spline-based model with 5 degrees of freedom. And let's store this as fit spline. Now let's compare. We have a model that was a linear model, and now we have a model that's not linear. So here's the original linear model, beta 0 hat, beta 1 hat. So beta 0 hat, beta 1 hat. And this is what you get when you ask for a curvy regression model by using a natural cubic spline with 5 degrees of freedom. It looks different. Instead of, well, it has an intercept, just like the linear model. But instead of just x, it has these ns terms, 1, 2, 3, 4, 5. This is like, it's as if we used a polynomial of order 5, in which case we would have intercept and x squared and x cubed, x fourth, x fifth. It's like that, except it's not that exactly. And instead, more complex mathematical expressions are in these columns that are called ns1, 2, 3, and 4, and 5. It's as if we used a power polynomial model, but it's not exactly that. So the interpretation of these coefficients, I don't know how to interpret these coefficients. Like, what is the 0.94276? If this was a linear model, I could say, well, that's the estimated effect of such and such. It's a mean change associated with a 1 unit increase in this variable and so on. Here, it's much more like a black box. All I know is I can represent my data reasonably well with a curve of this curvature using these coefficients. So let me show you how you actually get those fitted values, the predictions. Let's expand this a bit. And let's extract, or let's make predictions. Well, first let's overlay the estimated model. Then let's make predictions. We still have that scatter plot where the true model is there and the estimated linear model. If this is doing what we think it's doing, then whenever I overlay the fitted model, it should look a lot more like the truth than the linear one did. So let's overlay our model. This is going to require a little bit of off-the-cuff coding again. You don't have to know how to do what I'm about to do. But I need to make another plot function for the spline. And X needs to be the model matrix of my spline model. And then this needs to be the coefficients of our spline model. Spline coefficients. Model matrix of spline. All right, I think that should work. Let's try rerunning everything. Function did not evaluate to an object of length n. Okay. Oh, I know what I'm doing wrong. This needs to be NSX DF 5. Okay, I think that does it. Okay. Missing a column of ones. Almost there. Okay. So, simulated from the green curve, clearly not linear. We fit the linear model, that's the red curve, quote curve. And then the blue curve is our spline-based model. So it's not perfect. It looks like it doesn't capture the data very well in this region. The truth is the green curve, and our model dropped systematically below it. But it does capture a lot more of the curvature than the linear model did. If I was doing predictive modeling, I just tried a spline model with degree of freedom equal to 5. I mentioned we could tune this model. That would be something you would want to do if you were actually doing prediction with these type of data. Let's try using a smaller number of degrees of freedom, and let's try using a bigger number of degrees of freedom. And let's see which choice gives us the best fit of the data. You wouldn't generally do that by making pictures. You would do it by quantifying accuracy using something like mean squared error. But you could do cross-validation based tuning of this model to try to get that blue curve to fit even better. Let's see if we can make predictions before time runs out. The predictions from the linear regression model, predictions based on your model, that is, plug in the predictor values for the individuals you want to make predictions for to the fitted model. Beta 0 hat plus beta 1 hat times one of your individual's x values. So I can get predictions. One easy way to do it is with the predict function. Predict with the fit linear. New data is, if you do 1, that gives you, did you say 1? No? I thought I heard somebody say 1. I wonder what happens if I just say predict. Okay. So I have predictions from the linear model, and that would correspond to an MSE for the linear model. That is the average squared difference between the predictions and the truth. So we'll say y minus pred linear squared. I talked about the MSE in this week's Q&A, so there's a little more discussion of how we do this in the Q&A recording. I would predict, if we came down here and made predictions from the spline model and computed its MSE, that the spline would have a lower MSE. Just based on the picture, it looks like we did a better job of capturing the real relationship, and that should translate to more accurate predictions or smaller MSE. So I think here we could again say predict fit spline, and then MSE would be the mean of truth minus the spline-based prediction squared. The MSE for the linear model was 0.11, and the MSE for the spline model was a little bit lower, 0.08. So takeaway message from this nonlinear stuff. You're not restricted to linear models, even though they often work well, and they have good features being stable and interpretable. If your real-world data call for a nonlinear relationship, you have tools that you can do it with, whether it's with step functions or arbitrary curves. When you model something in terms of either step functions or curves, you get all the goodness of a regression model. You can interpret coefficients, or at least try to. You can do tests like, is X have an effect at all on the response? You can have interactions between the terms. And generally, when you have nonlinear relationships in reality, you'll get better accuracy, like lower mean squared error, if you use a model that allows for curviness. And as with all of our predictive models, these can be tuned by, for example, varying the degrees of freedom of the curve. And you can use train test splits or cross-validation for that. All right, I'll let you go. Next time, I'm going to show you tree-based models. These are quite a bit different from everything else we've done. They're not regression models, so there are no like beta coefficients. It's a totally different way of taking on the prediction task. It works for both numeric and categorical responses. Can be highly interpretable. Unfortunately, the more interpretable tree models tend to not be so accurate. Some of the most accurate predictive models out there are the more sophisticated tree-based methods. But the penalty, again, is that those are not very interpretable at all. They're very black box. Random forest is where we'll end with trees. That's a sophisticated tree-based method. Okay, I'll let you go. See you Friday. On Friday, I will finish, or I'll do the tree-based stuff, and I'll do a review and make some comments on what to expect for the exam. Exam on Monday. Okay.